I would like to welcome you on this new chapter where we are going to talk about C++20 modules. Modules are the last piece of the puzzle in what we covered in terms of C++20. It is one of the big features in C++20. We have already seen concepts, ranges, coroutines, and modules are going to be the main topic of this chapter. One of the main points in C++20 modules is to change the compilation model of C++ program. In all the C++ before C++20, we used to highly depend on headers to define things that we could include in other files and get our code to be reused. That way of doing things has a lot of benefits as time has proven, but it also has a lot of drawbacks, and C++20 modules were conceived to try and address those issues. One of the big points in C++20 modules is that you get tight control over what is exported from your module or what is not exported. So if you want a function to be visible, you export it. If you don't want it to be visible, you keep it inside your module, and users of your modules won't be able to see it. That's something you don't get by default if you use the old header-based compilation model for C++. Now, in the old days, you would have a header file. Here we have the math.h header file, and we would include it in a bunch of C++ files. When you get to compile your program, the first step would be for the preprocessor to take the content of this math header and paste it wherever it is included. And this would result in the same code being processed multiple times, hurting your performance in terms of compilation speed. And C++20 modules try to improve on this, as we are about to see. The header-based compilation model has a few problems. We have talked about compilation speed, but we also have ODR violations. If a header file is included multiple times, there are chances that the same definition is going to show up multiple times. This would cause a bunch of errors. There are cases where they include order matters and causes different behaviors for your program, and this is a headache if you happen to come across this problem. And as we have seen, headers don't offer encapsulation out of the box. Here is a piece of code that shows one of the problems you face if you use the header-based compilation model. And the problem is that a file you include has the capability to change the behavior of your program. Here we have a define. This is a preprocessor define. We are defining a macro here. And down here, you see that we have a piece of logic that does different things based on whether we have this variable here or this macro here defined. If it is defined, we run this piece of code. If it is not defined, we run this piece of code. And depending on what includes this macro here, your code is going to do different things. And this may be really bad. And C++20 modules avoid this problem in that macros are not allowed to be exported outside modules. So if I import a module, its macros won't be affecting what is happening in this file that imports a module. This is one of the problems that C++20 modules try to address as well. Here is an illustration of the same piece of code we saw before, but now we want to assume that we are using C++20 modules. The same idea applies really. We have the code in the module and we are including the same code in different CPP files, but the way C++20 modules work, a module file is not going to be processed multiple times. A module file is going to be compiled into a binary form, and any file that imports that module is going to be referencing that binary code. So we will process the module code once and get a binary form, and this binary will be used wherever this module is needed. So we don't have to process the module code to generate binary multiple times, and this is going to improve your compilation speeds. Try to think about cases where we have to include the same header maybe 20 times, 100 times. This is going to really make your builds fast. And there are some people that already report huge improvements in compilation speeds for very large projects. Now, if you use modules, compilation speed is going to be improved by the BMI, as we have seen. ODR violations are going to go away because declarations are confined inside the module. The include order problem is going to go away because the module is available in some pre-compiled binary format, and it is going to be included immediately where it is needed in your application. Another big benefit is that declarations are well encapsulated and you have tight control over what is exported and what isn't. Now that we have a few basics about modules, let's look at the actual structure of a module file. Your module file is going to start with this module thing, module semicolon. You really need this thing. And if you go down, you will have a module declaration. The syntax is going to be export module, and you specify the module name. Here, the module name is print. This is something you need to keep in your mind. And after your module declaration, you will have what we call a module preamble. The module preamble is where you put your import statements. In this case, we are importing the string header and IO stream. And after the preamble, you have the module purview, which is the meat of what makes your module. In this case, it is just a function, but it could really be any entity in C++. It could be a function, it could be a class, it could be a concept, it could really be anything. And as we go forward in the chapter, I will show you different ways you can use all those entities in the C++ 20 modules mindset, if I can say it like that. So a module file has three parts. The global module fragment is what is inside this module thing and the module declaration. In the global module fragment, you will have your includes, and yes, it is possible to still use the old header-based includes like we do here if it doesn't already support being imported like this, and I will show you a few examples of this. But now what I want you to focus on is the three parts that make up your module file: a global module fragment, the module preamble, and the module purview. Inside the global module fragment, you will have your includes or any other preprocessor macros. In the preamble, you have your import statements, and the module purview is what makes up the meat of your module. If you look down here, you see that we are exporting this print method function here. And this is what I meant when I said that anything you need exported outside the module needs to be explicitly exported. If you don't export this function, it won't be visible outside. If you want it to be visible, you have to explicitly export it like we are doing here. Okay, here are a few facts about the global module fragment. It can only contain preprocessor directives. It allows to include stuff the old way. And it is recommended to put your include statements in the global module fragment. If you put them elsewhere, you will face a few errors. And it is recommended to put them in the global module fragment. That's the idea here. The preamble is going to be containing your import statements. And the purview is going to contain the meat of the module: functions, types, classes, concepts, and really any other entities that you want to make up your module. Here are a few points I want you to keep in mind as we go forward. Each module is going to be compiled independently into an object file. So each module is a translation unit. And this is fairly different from what we are used to in old C++, where a header is really not a translation unit. Headers are included in the translation units. In C++ 20 modules, a header or a module is a translation unit, and it is compiled independently. Modules must be compiled in an order in such a way that all the dependencies are compiled first. So if a module is used by other modules, the one that is used by other modules has to be compiled first. If you are compiling manually on the command line yourself, you have to take care of this order yourself. And this is a really big headache if you have a big project. That's why we have to rely on tools like build systems IDEs to help us in taking care of these dependencies. In practice, you will be using IDEs and build systems to figure out this order automatically. Another thing I want to cover here is the extension that modules use. This is a confusing point if you ask me in C++ 20 modules. I would really have liked it if they had one extension for modules across all compilers, but in practice, every compiler is going to have its own preferences. If you are using the Visual C++ compiler from Microsoft, module files will have the IXX extension, the BMIs will have the IFC extension, and implementation files are going to have the CPP extension. This is the practice or the recommendations that we have to follow if we are using this compiler here. It is possible to use other extensions and tell the compiler to treat those as module files, but that's another step, and it would really help if we had good defaults that are supported across all compilers. If you are using GCC, GCC doesn't really enforce any extension. In many examples I have seen the CC extension. Clang has also its preferences. Module files will have the .cppm extension. Implementation files will have the CPP extension. And the BMIs will have the PCM extension. And we will get a chance to see this when we play with modules in a while. In this chapter, we will be using the IXX extension across all our compilers. And implementation files will be using the CPP extension. We will make sure to instruct our compiler to treat IXX files as C++ module files, and we will do that by passing special compiler options to GCC and Clang. This will allow us to compile the same source code across all compilers that we are interested in this course, and those happen to be Visual C++, Clang, and GCC. Now, before we head off and try to use these concepts in practice, I want to introduce header units. Header units are a concept we have to try and use existing headers as module files. For example, in all the C++, we are used to the IO stream header, we are used to the vector header. In module code, some people introduced the idea of being able to include these things or import these things as modules in C++20 modules. And a header unit is produced when your compiler tries to take an old header and compile it in a way that it will be treated as a C++ modules. They are part of an effort to make it easy to port all the code to modules. The compiler is going to compile the header into a form where it can be treated like a module. This is what we just said. And if you have used precompiled headers in all the C++ code, the idea is the same. They are precompiled in a way that we can treat them as modules. In this chapter, we will try to use the import keyword as much as we can, but sometimes that's not going to be possible because compiler support isn't there yet for C++20 modules, and you will see what we can achieve. The goal I have here in this chapter is to be able to compile the same code across all compilers. That means that sometimes we will avoid the good module practices to try and comply with what the weakest of our compilers support. So we will see more of this as we progress. Don't worry if this is not making sense yet. And where needed, we will revert back to including the old way in the global module fragment. Because of how groundbreaking C++20 modules are, for them to work properly, it's not up to the compiler only. We also need good module support in terms of the build system and the IDE. And at this point, the IDE from Microsoft Visual Studio, is the best when it comes to providing a good module experience. They have good IntelliSense, they have good support for the IDE, and everything feels natural. That's what I will be using to show you how to edit and compile modules. But once we have the code edited, we have the ability to compile the code using any other compiler of our choice. So I will show you how to also compile using GCC and Clang. Okay, the main compilers we are interested in are GCC, Clang, and Visual C++. In this course, I will be using GCC 13.20. It is what I get from WinLibs, as I have shown in the install videos. I would recommend you get the latest version. I will also show you how to use Clang 18. This is the latest version I can get of Clang, but this is going to be living in a Docker container. Don't worry if you don't want to use Docker. We will also show you how to use the Clang compiler coming from WinLibs. But in terms of Clang, you need at least Clang 16 for what we need to do in this chapter to work. So if you can't get it installed on your local system, if it is difficult for whatever reason, I would recommend trying out this Docker container. It is really great, and it gives you the latest features in terms of this Clang compiler. We will also show you how to use the Visual C++ compiler from Microsoft. And if you happen to want to use Docker, here are a few facts you need to be aware of. Here is a piece of documentation you can read to see how to use the Clang compiler with C++ modules. This is where I got the Docker image that I used, and I will be using the latest Visual C++ compiler and the Microsoft Visual C++ compiler. So these are the tools that I will be using to edit and compile my code here. If you want to use Docker, please make sure you have a good understanding of Docker. This is not a course about Docker. I will be showing you how to use it to compile C++. But if you really need to learn Docker, I would recommend doing more research in that regard. But I will give you a few pointers if you want to do what we do in the course. To be able to use Docker, you need to install it. So go to your browser and use your favorite search engine and see how to install the Docker engine. Once you have the Docker engine, you will pull the image. This is how you pull it. I will show you these things in a minute when we get to do them. You will need to change to the location of where your files are stored. In my case, it was in this sandbox folder. And you will need to run the Docker container. This is how I run it. And this V flag allows you to match the current folder in your host machine to a folder inside the Docker container. Once you have the Docker container, you attach a terminal to it and you can start running the commands that we will be running in this chapter here. Here is a fact I want you to take a moment to read. If it doesn't make sense, keep it in the back of your mind. This mainly comes from the fact that the name of the file where the module lives may be different from the name of the module. And Clang seems to expect the output PCM file to be the same name as the module name, but we will be using this flag to tell Clang to produce the name that we want in terms of the PCM BMI file. Again, don't worry if this sounds confusing. At this point, I want to try and run some module code and show you the tools that we will be using in this chapter here. Let's start with the Visual Studio editor. So I will open it, and the code that we will be using in this chapter is going to be coming from the course repository. So go there, go to this chapter, and you will find this code. I am going to click on Introduction here and open the code for this chapter or this lecture in the chapter. And you notice that we have two files. We have a math.ixx and a main CPP file. The math.ixx file is our module file. So this is what we will create in our project. And we have the main file that contains the entry point of our application. In each of these folders, I will also provide a README file, which is going to give you instructions on how to compile the code. At this point, I will show you how to use the Visual C++ compiler, GCC 1320, Clang 16 that I have access to from WinLibs on my Windows machine, and Clang 18 coming from the Docker container. So make sure you have this code. It is going to be what we use in this chapter here. Once you have Visual Studio, we will create a new project. So create a new project. It's going to be a console application, and we will choose the location of this. Let's change this to go somewhere we want to go. So we need to go to, for me, it is going to be Sandbox, and go to 49 modules. This is going to be the folder where my projects are going to be stored. And I will specify the name of the project to be the same as from my GitHub repository. So let's come back here and put in the name of the project. It's going to be 48.1. And I want to place the solution and the project in the same directory. And this means that this is going to be the full path of the project as shown here. Once you have what you like, click Create. This is going to create a project for you. It's going to be a blank C++ project. And the first thing I want to do is to rename this to main.cpp and clean up the code here. I think we don't need all this junk. So, and we want to import IOStream because we are using modules. So import IOStream. We don't use include anymore. And for this to work, you need to enable C++20 for this project. This IDE is going to be using C++ 14 or 17 by default. So let's enable C++20. You do that by clicking on the project here, right-clicking, go to Properties, choose C and C++, go to Language, and choose C++ Language Standard to be C++20. Once you have this, I also want you to go to General on top here and select Scan Sources for Module Dependencies. Here you will select Yes and click Apply and click OK. And now our project is ready to start using C++20 modules. If you go back to the GitHub repository, you will see that what I just did is described in these instructions for the Visual C++ compiler. So if you are ever confused, make sure to come back to this README file and read about it. I will be putting it in this folder when I push to GitHub for this course here. So let's try to compile. We can do that. So build the solution and see what we get. You see that build succeeded, one failed. Why is that? We don't have a closing curly brace here. So let's make sure we have it and build again. Now the build is good. We can debug, start without debugging, and this is going to say hello world. Let's create a module file. Now that we have a project ready for C++20 modules, you create a module by coming to the project, right click and hit add and say new item. And if you do that, you will be given the option to create a C++ module interface unit. This is what Microsoft calls them. It doesn't really matter. Ours is going to be called math.ixx, and we add it to our project. And we have seen the structure of a module file, but I would recommend even coming to GitHub and copying our math.ixx file here. You see, it is the same code we saw in the slides really. So you can click here to copy raw file and come back to our IDE, take out everything and paste in our module code. So we have our module thing, we have our module declaration. Here I want you to see that it is possible to name the file containing the module and the module differently. This is something I do a lot for my own personal reasons, and I thought I should show you this if it happens to make a difference for whatever it is you are trying to build. So here is our global module fragment. Here is our module preamble, which is going to contain our imports. And down below, we have our module purview. Once we have a module, we can use it to do all kinds of crazy things. For example, because we are exporting this function, we want to call it where this module is imported. Now that we have the module, we can import it. We don't need to import IOStream at this point. We want to import math, and we want to call this say something function here. So let's do that, say something. Okay, once we do that and try to build, let's build a solution and see if it works. Could not find module math. What could be going? It's not called math. You see what I did here? It's called my math module. Okay, so I need to go in the main file and provide the name of the module. What you import is not the name of the file, is the name of the module. And this was an error, but it was a lucky one because I get to emphasize this for you. Otherwise, some of you would have made the same mistakes. So import my math module. This is what we import. Once we have this import here, we will have access to anything that is exported from this module file. Now that we have this, we can try and build. Okay, if you get 1 succeeded, 0 failed, it means your compilation was successful, and you can try and run this. So debug and start without debugging, and we have saying something, which is what we printed in our say something function here. Now, notice that we are importing IOStream. This is what is called a header unit. This is what C++20 provides to be able to use old headers in C++ as modules. This is not always going to work on all compilers, but the idea is that they should work, and we should expect this to work when we have good support for modules across all compilers. Now we have compiled our module code using the Visual C++ compiler. It is possible to do this on the terminal, but I thought it was a waste of effort because we can do this easily through the IDE. If you are on Windows, I would recommend using Microsoft Visual Studio at least to edit your module code, because you can see that we don't have a lot of errors, IntelliSense is there. It really provides a good experience. But if you are on another operating system, don't be discouraged. You can still type your code and compile it on the terminal as I am about to show you. If we go back to our README file in this lecture here, you will see that we can also use GCC 13. This is what I get from WinLibs. So let's go there and say WinLibs. And if I go there, if you remember from the install section, this is what we used as our compiler. It provides GCC 13.2.0 at this point, and it also provides Clang 16.06. I have this installed on my local system, so from the Visual Studio editor, I can come to view and do terminal. This is going to open a PowerShell window for me to use right inside this editor here. Okay, we have a PowerShell here. I can say G++ version, and it is going to show me which version I have installed, 13.2.0. I can even ask the Clang version I have installed, and it is going to give me the version here. So you need Clang 16 to be able to do what we want to do here. And I would recommend getting the latest version of GCC you can. If you are on Windows, you can use WinLibs like we are doing here. So let's go back to our Git repository and see how we can use GCC. You see the input files are still what we had before. We have the IO stream header unit that we need to compile before we compile any other thing. But we also have math.ixx and main CPP as the input. If you go where our project is stored, where is it stored? Let's go there. Okay, introduction. You see that we have a lot of noise coming from the Visual Studio editor, but the main thing really is the main CPP file and the math.ixx file. And in this case, we will try to compile directly using the G++ compiler. Let's grab the command here. I don't want to type it because I may do errors and have typos that waste our time here. Let's do ls to show the content. You see we have the main CPP file and the math.ixx file. This is what we are interested in, and the rest here is really noise that Visual Studio uses to set up this project for us here. But now we can compile the main CPP file and the interface file. With the GCC, the first thing you have to do is to compile the header unit. So let's do that. We copied the command from GitHub earlier. This is the command g++fmodules-ts. You tell it that you are compiling a C++ system header, and you specify the header that you want to compile. Once you hit enter, this is going to generate a BMI for the IO stream header. And if you do ls, you see that we have generated a GCM cache folder here. And this is what is going to contain your BMIs. Let's go and grab the other command. So we can grab the other command, which is going to compile our interface file. So let's put that here. And if we do that, this is going to also compile this interface file, and you see that we have an object file as a result of running that command. And the last command is going to link our executable, and the executable is going to be named rooster.exe. So let's paste the command in here, and if we do ls, you see that we have a rooster.exe file. If we run it, it is going to say saying something, and we have successfully compiled our module code using Cplusplus 20 modules through the GCC compiler. If you want to use Clang, again, I provided these instructions that you can follow. This is the Clang version that we have on Windows, but on Windows, I couldn't use PowerShell, and I resolved to using the command prompt for this to work properly. Let's try to use PowerShell and show you the problem that I got. So let's copy this. Okay, for Clang, Before we do any further compilation on the terminal, we should remove the noise that we introduced. Let's remove any object files that we generated. And let's remove the GCM cache folder. And also remove rooster because we don't need it. And we will try to use the instructions here to compile with Clang. Let's copy the command as we did earlier. Try to compile. Okay. This is going to try and compile the IO stream header, okay, as a header unit. The same idea we had for GCC ready. This is going to run. It's going to give you a warning. This is because Clang is really in experimental support for this. Don't worry about this warning at this point. Once we have the header compiled, we will try to compile the IXX file. Let's talk about the command a bit. Here you see that we are using Cplusplus20. We will tell it the location of the IO stream BMI that we just compiled, and we will tell Clang to treat any IXX extension files as C++ modules. This is what this command here does. We will tell it to compile and output a file named mymathmodule.pcm. And if you come back to our code, let's open Visual Studio. You see that the module file is named math.ixx, but the module is named mymathmodule. Clang expects all BMIs to be exported in the name of the module. That's why we are using this name to output our PCM for our module here. This is something you need to keep in mind if you are using Clang. So let's copy the command and put it in our editor and see what we get. So copy. And let's paste this. So this is going to compile our PCM. And you notice that it is saying no such file or directory PCM. This is the problem you face if you try to use the Clang compiler in PowerShell on the Windows system. But this is going to work if you use the terminal. So let's clean up whatever we just generated here. So let's do ls and see what we have. We have a PCM file here that we don't want, that was generated earlier. So let's remove any PCM files, and we want to start a terminal window. Let's start a developer prompt, okay, which is going to allow us to run the commands for Clang here. So let's do that. We will start over and use the first command to generate our header unit. So we can paste this in. It is going to generate our BMI. Let's go back and grab the second command. We put that in here and it is going to compile. You see that we have no error. This means that our PCM was generated. And if you go in here and do dir, because we are on the command prompt, you will have our mymathmodule PCM file generated. Let's go back and grab the third command, which is going to compile our main CPP file into an object file. So go back to the editor and hit the command. We grab another command and compile to generate an object file for our module. So let's do that. Paste and run. If we do dir, we will have our object files, and all that remains is to link everything together and create an object file which is named rooster. Let's do that. We can come back to our terminal and hit this, and if we do dir, we should have our output file named rooster. If we run it, it is going to saying something, and we have just successfully compiled our module code using the Clang compiler on Windows. I will also show you how to use the Docker container because I can. I really like this because it gives me access to the latest compilers, but if you don't want to go through Docker, you can do what we have just done in this chapter here. But if you happen to be on a system where it is inconvenient to install or build the latest compiler for yourself, you can use Docker. It is really going to give you access to the best tools here. So what do we do to use Docker? The first thing you have to do is to install the Docker engine on your system. So make sure you have it installed. If you don't know how to install it, you can go to your browser and say install Docker. and you will have a bunch of results here. You can go through this, install it on your system. Once you have it installed, you will be able to go to your terminal, whatever really. So let's use developer PowerShell here and say Docker version. It is going to show you the Docker version once you have this installed. After you have it installed, you will need to pull the Docker image. And what we want to use is this Docker image here, Clang Ubuntu, and we want to pull the tag for 18. So let's go to Docker Hub, where you pull Docker images from. So let's do Docker Hub, and let's search for Tix99. I think that's the name of the user, Tix99. So Tix99 Clang Ubuntu. Okay, I think this is the container. Once you are here, you can pull this container and use it. You see they have a bunch of tags. They have 18, which was pushed 21 days ago. You can see this is really new. Yeah, you can use it if you need the latest Clang. Once you have Docker Engine installed on your local system, you can pull this image and use it. And we even have a command here you can copy to pull it. I have it already pulled, so I don't need to pull it again. But if I paste that command here, you can see that it is saying docker pull tix clang ubuntu 18, which is exactly what I showed you in the slides. So you pull it. Once you have it pulled, I would recommend changing to the location where you have your project. In this case, I changed to the dsandbox folder because I have a lot of things installed there that I want to manipulate through my Docker container. Once you have a location you like, you will run this command here. Let's show it in big format so that you can really see it. You say docker container run, and you will specify the name of your Docker container. In this case, it's Clang, and I specified Hank because I watch a lot of Breaking Bad. You specify a flag to say that it is interactive, and the v flag here is going to map a local folder to a folder inside the container. In this case, the pw command is going to pick the location where I am, and it is going to map to a location inside the container, which is home Gakwaya in this case. After that, I specified the name of the container that I want to run. Again, this is not a course about Docker, so I just show you the commands that I use on Windows. This may be different on Linux or a Mac, especially on this command here. So if this gives you problems, please check and do more research on how to make this work on your operating system. Once you have this running, you can attach a terminal to the Docker container. In my case, I have Docker installed and I already have pulled this image. So what I can do is Docker container LSA to show the images and containers that I have. You can see that I have Clang Ubuntu. It is the same container that I just talked about. And I can start it. I start it by saying Docker container start and specify the name of the container, which happens to be Clang Hank here. So Clang Hank, and I start it. It is started. Once I have it started, I'm going to attach this terminal to it. And I do that with Docker container attach Clang Hank. And once I do that, I am inside the container on this terminal here. If I do uname A, you see it is a Linux box that I have access to from inside Microsoft Visual Studio, and this is really cool. So let's change to home Gakwaya, the directory that I mapped. And I mapped this because it contains all of the projects I want to play with in this container here. Let's change to the Cplusplus 20 masterclass, the source code for this chapter here. And let's do ls to find the code, cd 49 to go to our chapter here, and do ls cd 48.1 for the introduction here. And if I go there, I have access to everything inside the project that we are working on inside Microsoft Visual Studio here. Let's do lsalh to see everything. You see we have our Visual Studio files. We also have a few things earlier from building with Clang on Windows. Let's take out all this noise except for the Visual Studio project because we are still using this inside Microsoft Visual Studio. So we can remove any object files, and we can remove rooster, and we can remove any PCM files. PCM. And if we do it lsalh, we will see that we have the main files of interest for this project here, the main CPP file and the math.ixx file. Even if we are working inside the container, we are still manipulating these files here, and this is really cool. Okay, now that we have this, we can run the commands to compile inside Docker. You see, it is the same thing as we did for Clang 16, but because we are on Linux, we are making sure to use the C++ standard library that comes with Clang. This is what this flag here does. The rest is really the same, so let's grab the command and copy it and put it inside our container. Hit enter. This is going to compile our header unit. Let's grab the next command. And again, I will share this file as a resource to this lecture, so you can copy these commands and use them as I am using them here. Don't worry about typing all these because you may introduce typos that are going to eat a lot of your time. We have done this, so let's run the next command. This is going to compile our main file into an object file. So let's put this here. And we will grab the other command, which is going to compile our module file. So let's do that into an object file. If we do ls, we have our object files. And the last command is going to produce our binary. Let's copy this and put that in our terminal. And we hit this, and this is going to generate our rooster binary. On Linux, you run it like this, and it is going to say something exactly as we expected. And this is really all I wanted you to see in this lecture, giving you an overview of how you can compile your module code using the main compilers that we are interested in this chapter. We saw how we could use the Visual C++ compiler from Microsoft. We saw how we could use Clang, both 16 and 18. We used the 16 on Windows, and on Windows you have to be careful to use the terminal because it's going to give you an easier time. PowerShell has problems that I don't want to get into, and we saw how to use the GCC compiler. Now that you know this, we can head over in the next lecture and build our very first module file. Go ahead and finish up here and meet me there. In this video, you will get to build your very first module. The last lecture was really giving you an introduction to the structure of module files and a bit of a background on C++20 modules. But in this lecture, we will start to try and actually use them. We will declare a module file. The name of the file is going to be math.ixx because this is the extension we are using here. And notice that in the global module fragment, we are using old style includes. Some things can't still be imported, especially on different compilers. I think you can import almost everything inside Visual C++ at this point, but it is not always going to work with GCC and Clang. What I have here is the sweet spot I was able to find to work across all compilers, but feel free to try and import and see how far you can go in your favorite compiler. If you come across errors, please revert back to what we have here because I made sure it can work on all compilers of interest in this chapter here. After these includes, we have the module declaration. Our module is going to be named math stuff. It is a module declaration because we have export module here. If we don't have the export keyword, it's not a module declaration. It is something else, as we will see later on as we progress in the chapter. After this, we have our import. IOStream can be imported across all compilers, so this is going to work. And after this, we have the module purview. In this case, our purview has three functions. We have add, greet, and print name length. And all these functions use different facilities from the thing we either include or import here. Add is going to return the sum of two numbers. Greet is going to print a message, and it is going to try and use std string because we included it here. And the print name length is going to use features from the C string header that we just imported here. And if we import this module file, we should be able to use either of these functions here. and it is going to work in a minute. Okay, here is the main CPP file that tries to import our module. Notice that we are also importing IOStream because we are trying to print things out here. A few facts before we try and run this code here. If a module declaration has an export in front of it, the file containing the module becomes a module interface file. Per that statement, if we go back to our code here, the line here makes this file a module interface unit because it is a declaration of a new module in our C++ program, if I can say it like that. The collection of entities exported from a module file make up the module interface. So in this case, our interface is made up of three functions: add, greet, and print name length, because it is what we export from this module here. This is what we mean. Okay, now that we have a few basics out of the way, let's zoom out a bit and see different ways we have to use modules in our C++ program. The first is include translation. And include translation is what we are doing in our global module fragment here. You will include files as you would have included them in all the C++. And the C++ compilers are configured to handle this in a specific way to make it usable inside your module code, and this is called include translation. The other option is header importation, which is what we have been doing all along. If we go back to our code and look at line 8 here, we are doing header importation, and this is what we call a header unit in our C++ program. C++ compilers will compile this header file in a way that it can be treated as a module. That's why we can do this. And the other way is module importation, which is what we have been doing. Once you have a module defined, you will be able to import it like we are doing in our main CPP file here. This is module importation. So we have three ways: include translation, header importation, and module importation, and you will use whatever makes sense for what you are trying to build. Okay, here are a few facts about each of these ways to work with modules. I will let you pause and read about them because it is what we just said. And now that we have these basics, we can actually try and run our module code here and see what we get. Again, as we have done in the last lecture, we will be using the Visual Studio IDE as an editor, and we will be able to compile this code either using Visual C++, GCC, or Clang. And you don't really have to use all these compilers. Use whatever you are able to access on your local system, but I would recommend to at least try a few of these. In the first few lectures of this chapter, I will be compiling with you, but after you have the hang of it, I would expect you to be able to compile by just copying these commands and putting them in your terminal. I will always show you how to do this in the Visual Studio IDE, but when I can't, but to save on time, I may just show you the instructions here and let you compile on your own. We will see what time allows. Let's go to our editor and create a new project and create our new module here. Let's grab the name and steal it. So it is going to be 48.2, your first module. I will create a new project. So file, new project, and it is going to be a console application, and I'm going to give it a name and create it. Save what we had before, and we want to rename this to be main.cpp as we always do. And what else? We can create our module file. So new item, it's going to be a module unit. It's going to be named math.ixx as we always do. And we can steal the code. If you want, you can type it, but I am just going to grab the code I have on GitHub here because it's going to be easier. I can copy the raw content, come back in my editor and put in the content. And you can see that we have squiggly lines because we haven't enabled modules. To enable modules, please come back to the project, right click, go to properties, go to C and C++, choose language and choose Cplusplus20. This is going to enable modules for you, but you also need to come to general and go to scan sources for module dependencies and set this to yes. Click apply, click OK, and our module should be understandable by the IDE right now. Again, we are not doing anything special. We are just following the structure to create a valid module file. We have our module declaration. On top here is the global module fragment in which we are using old style includes. And in our module purview, we have the exported entities from our module. In this case, again, it is the add function, the greet function, and the print name length function here. Let's grab the code for the main CPP file. So let's grab it, copy row file, come back to our editor, go in main.cpp, control A to remove, and paste in the new content. And if we try to build this, let's try to do that, build solution. And if we run the program, we should see the result here. So debug, start without debugging, it is going to print whatever it is we expect here. Now we have this running using the Visual Studio IDE. We can use any of the other compilers we have access to. On Windows here, I have access to a GCC compiler. Let's create a terminal window that we can play with. Okay, now we have our PowerShell window. You can see that it is working in the current directly. Again, if you missed this, I got this by going to View and choosing Terminal here. This is going to open this window for me. And now I have the main.cpp file and the IXX interface file here. We can compile these using any of the supported compilers. If I go back to the GitHub repository, I have instructions to use any of the other compilers. This project is made up of two files, as you see here. If we try to use Cplusplus, we can copy the first command here, come back to our IDE and clear and see the version of Cplusplus that we have. You can do this if you want. And we will paste in the command to compile our header unit because it is the first thing that is needed and other files in the project are going to be depending on it. Let's grab the second command to compile our interface file into a C++ file. Again, what we are doing here, we have an option that we are passing to the C++ compiler to treat this file as an interface file, and it is XC++ as you see here. The same idea we really saw for Clang. Let's grab the command, copy, and go back to our PowerShell window and put it in. If we do ls, we should see our object file, and we should see a GCM cache folder that was created. This is what contains our module files or our BMIs, if I can call them like that. We can cd into there and see what we have. So let's cd GCM clear and do ls. You see that we have math stuff here, our BMI. If we change into the C folder, we can go there. Why not? And do ls, you see we have MinGW. If you change into this MinGW, you will eventually find the BMIs for the header units that you generated. I don't really want to go there at this moment because this is compiler specific. Now that we have the object file, we can link it. So let's do that. Grab the last command to do that and put that in the editor. And now we should have a rooster file, as you can see right here. So we can run it. We can say rooster, and it is going to give the output that we expect from the methods that we defined in our module interface file. Okay, this is how you compile this using the GCC compiler. You can also use Clang on Windows, but you need to do this from the terminal. So let's grab the first command here and come back to our terminal window, developer PowerShell. Let's remove whatever it is we had. So remove r.gcm. We need to let go of that. We also need to remove any object files that we have generated. Can't type, can I? So we have that, and we are clean again if we remove the rooster file. Now we can go to the command prompt and pass the commands. Again, if you are using the Clang compiler on Windows, you need to go through the command prompt for reasons that we have seen in the first lecture of this chapter. So let's put the command here, making sure we are doing this from the command prompt. This is going to generate our header unit. Let's pass the second command, which is going to compile our module into a PCM file, which is the BMI format for Clang. Let's grab the third command, which is going to compile our main file into an object file and put that in our prompt here. This is going to give us the object file. Let's grab the other command, which is going to compile our module into an object file. Again, it is going to give us the object file here. And the last thing is going to link everything together and create a binary named rooster. Let's try to do that. And now we have a rooster file that we can run. If we do rooster, it is going to run, and we have the results here. You can also use the Clang compiler, which is embedded in a Docker container. For that, let's create a new PowerShell window, and we will connect to our Docker container. Let's do that. Docker container Clang hack can do that. And now we can cd up and go into 48.2. This is going to take us in the current project, and we can run the commands to compile with Clang. Let's do ls-alh and remove any PCM files and remove any object files and remove rooster. Now we have a clean slate from which we can compile using the Clang compiler embedded in our Docker container. Again, the commands are here, so copy the first command, which is going to compile our header unit. Let's put that in here. And we want to grab the command that is going to compile our module. Let's put that in our terminal here. Grab the command that is going to compile your main file. Put that in the terminal here. Grab the command that is going to compile our module into an object file, and we put that in place. And the last one is going to put everything together and create a binary named rooster. So let's do that. And if we run it, it is going to give the expected output here. Again, you don't have to use all these compilers. I am showing them all so that you have options, especially if the Docker option is confusing to you. Use whatever compiler you have access to, but I want you to have as many options as possible. This is really all I had to share in this lecture, showing you a good example of how you can create your own module. Our module is made up of this interface, and an interface is made up of things that you export from your module. I am going to stop here in this lecture, and I will see you in the next one. In this video, we are going to see that you can actually block a lot of entities inside a single export block and make it easier for you to wrap everything together. This is just an alternative to what we have been doing before, where we explicitly added the export keyword on anything we wanted exported. You can set up an export block like we are doing here and put everything inside. This is the main point of this lecture here. Once you have this defined, you can import this module, and you will have access to things that are inside the export block here. I hope this makes sense. Now that you know this, let's create a project and play with us. Okay, here we are back in Microsoft Visual Studio. We are going to create a new project. It's going to be a console application, and we will name it 48.3 block export. It's going to live in whatever location you put it in. Mine is stored at this full path here. This is going to create our project. We can rename the main CPP file. So main.cpp, and we need to enable Cplusplus 20, remember. So let's go to the settings here, go to language, enable Cplusplus 20, and we need to go to general and scan sources for model dependencies and say yes here, apply and okay. And we can create our module file, which is going to be named math.ixx, I believe. So let's do that. Math.ixx, add a new item. It's going to be a module. Let's name it math.ixx, add it. And we are going to hop over to our GitHub repository and grab the code for the block export lecture. So let's grab the interface file. We can copy the raw content and come back to our editor, and in our module, take out everything and put in our module. And what I want you to see is that it is the exact same code we had in the last lecture, but we are setting up an export block, which is going to export the add function and the greet function here. And this is really all. Now that we have this, we can also grab the code for the main CPP file. Let's grab it, copy, and put that in our main.cpp file in our project. Take out everything and put in our code, and all the squiggles should go away. Now we can run debug start without debugging, and it is going to give the output here. Again, it is the same thing as the last lecture, only now we are using a block export to export the add and greet functions here. The rest is really the same. The compilation steps are the same from the last lecture. I have them listed in this README file. If you want to use GCC, these are the instructions. If you want to use Clang, these are the instructions. The steps are shown in the last lecture. I'm not going to repeat them here. Try to build this on your local system and see this running. This is really all I had to share in this lecture. I hope you found it interesting. We are going to stop here and I will see you in the next one. In this video, we are going to see how we can separate the interface from the implementation. And we will be doing this in the same interface file. Let's look at the code because that's how it's going to be easy to see. Here we have a module file doing what we have been doing all along. We have our module thing, we have our declaration down here, and we have our module purview. But in the purview, if you look carefully, you will see that we just have declarations. We don't have implementations. We have the add function here declared, the greet function, the print name length function, but the implementations are nowhere to be seen in this export block. And this is one way you can organize your code. The implementations are still going to show up in the same file, but they won't be in the export block. I have to say that this is one way you have to organize your code. We will see other ways, including separating things in separate files, and you will have to decide on what works better for your case. Now that you know this, I think it is high time we headed over to our editor and saw this in action. Okay, here I am inside Microsoft Visual Studio, the IDE or editor we chose. I already have a project created so that we don't waste time creating it, but I have to make sure to show you that you have to enable C++20 for modules to work. We go to properties, let's do it together. Let's not be too fast. So right click on the project, do properties, go to C and C++, choose the language and choose C++20 here. You also have to go to general and go to scan sources for module dependencies and set this to yes. This is the requirement for what we want to do to work inside this IDE here. Now that we have this, we can create our module file. Let's go to add new item, and it is going to be a module interface unit. We are going to name it math, and it is created now. And as we always do, we will go to the Git repository. Please go to this chapter under this lecture, separate interface from implementation, same file. And we have the files that make up this project. Open the interface file and copy row to copy all the content in this file, and we will put all this inside our newly created module file here. So I am going to paste this. We have the global module fragment, we have our declaration, we have our export block, which only has declarations and no implementations or definitions, and implementations will show up on the outside below this export block here. This is one way you can organize the code inside your module file. Please notice that for the class, we only have the class definition, but the implementations for the methods, let's see, we have a constructor which is not implemented in the class. This is what I wanted you to see. This two-parameter constructor here is implemented on the outside in this implementation section inside this module file here. The rest is really what we have seen before. Nothing more to explain here. We have our includes, we have our import. Again, if you have an import like this, if you are compiling manually, you have to make sure to compile this header unit first before you compile things that depend on it. I hope you know this by now. Let's go to the Git repository and grab the code for the main file. Let's copy it, come back to our IDE, delete whatever we have in here and paste in the new code. Now I think we can compile, but before we do, notice that we are importing math stuff. Math stuff is the module we declared here, and we are able to use it in the main file here. This is all I want you to see. Let's try to build the solution, and the build is good. Why are these squiggles not going away? They went away, and we can try to run start without debugging, and it is going to give us the expected result here. This is how you can separate declarations from implementations in the same module file. Now that you have seen this, the next thing I'm going to do is just to show you how to compile this on different compilers. If you don't care about that, you can stop here and go to the next lecture. But I strongly recommend to see all these little nuances of how you compile on different compilers. So let's go to the Git repository, open the README file. We will see that we have the option to compile with GCC. I will be using GCC on my Windows machine here. So let's do that. Let's come back and go to PowerShell. And we are in this project. This PowerShell window is opened in this location of this project here. And I have access to G++. If I do this, it will show me the version G++. If I can type today, it's going to show me the version. So let's try to compile this. Before we compile, you can ls to see the content. You see that the main files we have are main.cpp and math.ixx. The rest here is the noise that the IDE, Microsoft Visual Studio, is using to set up the project here. But the main meat of this application is these two files. So let's pass the GCC command to precompile our header unit. It is going to pass. Let's come back to the Git repository and grab the other command, which is going to compile our module file. Let's copy that, go to the terminal and paste that in. Let's go back and compile the main file and link into the Rooster executable here. So we can grab that and paste that in here. If this goes through, it is going to give us a Rooster file that you can see down here. And if we run it, it is going to give us the expected result. And we just compiled using the G++ compiler on Windows. Let's try to also use Clang on Windows. But if you remember what we have done before, we have to make sure to use the command prompt. We don't have to use PowerShell because PowerShell is going to give us problems we don't want to deal with. Let's grab the first command here. And I am going to hop over to my command prompt. But before I do, let's clean up what we had before. So let's do ls to see what we have. We have an object file that we don't want. We also have Rooster. So let's remove Rooster and remove any object file from this folder. And it is clean now. We also need to move the GCM cache folder. So let's remove that. It was generated by GCC and clear. And we can come back to our command prompt and run the command to precompile our header unit IO stream. Let's pass that. It is going to give us a warning that we are going to ignore for now. The important thing is that it works. We need to compile our module file. Notice that we have to make sure that the output PCM file has the same name as the module that we are declaring in our file here. This is really important. Again, if we come back to the file, notice that the module name is math stuff, and we have to make sure that the output PCM file also has the same name as shown here. I hope you can see this. Run the command. It is going to do what we want to do. If we do ls, let's do dir because we are in the command prompt. We should have our PCM file, which is generated. You can see it right here. Let's go back and run the next command, which is going to compile our main file into an object file. So we grab the command, we put that in here, and it is going to give us an object file. dir, we should have the object file generated right here. We are making progress. Let's come back and compile our module file into an object file. This is the command to do that. We put that in place, we run it, do dir. It is going to be available right here, the object file that we want. We go back to grab the last command, which is going to put everything together, and it is going to give us a Rooster binary that we are looking for. Let's run the command. If we do dir, okay, now that we have the Rooster file, we can run it, and it is going to give us the expected output. This is how you can use the Clang compiler on Windows to compile this project. We can also hop over into our Docker container. I have it opened in this developer PowerShell here. Okay, so this is inside my Docker container. If you don't know how to set it up, please watch the first video in the chapter. I showed you instructions on how you can get this set up, just like I have here. Let's grab the first command, So which is, the steps are really the same as for Clang 16 on Windows, but we made sure to use the standard library that comes with Clang. Before we even do anything, let's do ls and remove any PCM files that are generated in this folder. Let's remove any object files as well and remove Rooster. And if we do lsalh, we're going to see our clean folder with some noise coming from the IDE that we are using, but we are just going to ignore this. The important thing are, what we really are focused on are the main CPP file and the math ixx file here. Let's go down and put in the first command, which is going to pre-compile our IO stream into a binary format. So IO stream.pcm. This is going to go through. It should give us a warning, but we're going to ignore that. Let's go down and compile our module file into mathstuff.pcm. This is what Clang expects. We put in the command, we compile, and let's grab the next command. This may seem repetitive, but I really do encourage you to do this because this is going to give you an understanding of how these things work, especially the order in which you have to compile things. And these are things, tools like the build system, the IDE are going to be helping you with. Let's go back and grab the next command, Clang, to compile the module into object code. So we put that in here and it is going to compile. And we need to put everything together and compile a binary that we can run on Linux. Let's do that. And this is going to go through. If we do lsalh, we will see all the output here. The most important one being the rooster binary that we can run by running this command here, /rooster. If we run it, we will have the same output we've seen all along. This is really all I had to share in this lecture. The main idea being that you can separate declarations from implementations, and this is going to make your code a little more readable. This is a decision you will make. I will show you different ways to organize your module code, and you will choose whatever works best for your use cases. I am stopping here in this video, and I will see you in the next one. In this video, we are going to go one step further and store our implementations in a separate file. If you remember, in the last lecture, we separated things. The declarations were living inside the export block, and the implementations were put below the declarations, but still in the same file. In this lecture, we will be separating those two things and store them in separate files. Here is how our interface is going to look. It's nothing different from the last lecture. We have our module thing here. We have our export that declares our module. We have the preview, which contains things inside our export block. We have a bunch of functions, and we have a class named point here. And all this is going to be living in an interface file. I think it is going to be named math.ixx, and the implementation is going to be living in a separate file. Here is our implementation. You can name it whatever you want, but notice that it is living in its own file. Now, one thing you have to notice when you have an implementation file like this is that the declaration doesn't have the export keyword. And this means that this is an implementation file. It is not declaring any new module. It is just a file that may be adding some capabilities to a module that has already been defined somewhere. And a module is only defined in a module interface unit, as we have here. How do we know this is a module definition? Because of the declaration line we have here. It has to say export module and specify the name of the module. And because we have this line here, this is a module interface unit. The others will not have that export keyword. They may say module and say the name of the module, but they don't have the export keyword. And this means that this is not a module declaration. It is just a way of reusing a module that has already been defined somewhere else. With this out of the way, we have the global module fragment as we have in other module files. We have the preamble where we can do imports, and we have the preview, which is going to be containing implementations in this case. Again, we are implementing the add function, the greet function, the print name length function, and a few methods from our class. Now that you know this, we're going to head over to our IDE and see this in action. Okay, here we are inside Microsoft Visual Studio. I have the project already created, but again, I will show you that for this to work, you have to enable Cplusplus 20. So let's hop over in the properties and enable Cplusplus 20 here. And we have to go to General and enable Scan Sources from Module Dependencies. We have to turn this on and apply and hit OK. And the files we will be using are stored in the GitHub repository. Again, the project is 48.5 here. So read through this if you want. And you notice that we have a bunch of files. We have the interface file and we have the implementation file. It is named math.impl.cpp. This is a name I just chose. You can name it whatever you want. And we have the main CPP file. So let's create these two files here in our project. We can go back and say add new item. It's going to be a module file. So math.axx. We haven't done the implementation file yet. We have our module file and we need an implementation file. It's going to be a CPP file. So choose CPP on top here and name it math_impl, IMPL. If you do add, you will have the file generated here. If you want, you can type this, but I do recommend using the code from GitHub. And starting from there, you can modify it to be however you want. This is going to avoid typos that would waste a lot of your time. Let's copy this and put this inside our math interface file. So let's do that. So we have our interface again. It's everything you have seen before. Let's go back and grab the implementation file, math_impl, and we will copy this, put this inside the implementation file we have in our editor or IDE, and we need to change the main CPP file. Again, we will grab from the GitHub repository, put it in, so copy, come back here, and put it in. We take out whatever we had in by default, and we put in our new code. And I don't think we copied the right file here. Let's go back and make sure we copy raw file. Okay, and come back to our main file and put in the content. Now we have the right content. Let's make sure we have everything as it should be. This is an implementation file. Export. This is a module declaration file, so this is right. The implementation file shouldn't have an export keyword here. And we have, what did we do? Math_impl. This is, the implementation file wasn't copied correctly. So let's go back again and make sure we copy raw file. And we can come back here and make sure we have the correct content inside. Okay, now we should have the correct content, but let's double check anyway. We have the interface file with export module here. The implementation file should just have module and have the implementation for the functions and the constructor. And the main CPP file should import our module and try to use it like we have been doing all along. With this in place, let's try to build and see what we get. Okay, the build is going to be good. Now, one thing I want to draw your attention to that I haven't been doing before, I should have showed you that, is that the first step the compiler goes through is to scan sources for module dependencies. You see here, it is scanning the implementation file, the interface file, and the main CPP file. And once it looks at all these files, it is going to figure out which files depend on which, and it is going to compile the dependencies first. Notice that when it starts compiling, it is going to compile IOStream first. After that, it is going to compile our interface. After that, it is going to compile the implementation file, and after that, it is going to compile our main CPP file. You notice that these dependencies are figured out automatically by the IDE and the build system behind it. I have to say that for Microsoft Visual Studio, it has its own custom build system. I believe it is called MS Build, and it is what is doing all this magic you see happening here. But if we happen to compile manually, like we do with Clang and GCC, we have to figure out this order on our own. Let's go to our README file and see the instructions. We just did what is needed for Visual C++ on Windows. If we try to use GCC, notice now that we have multiple files. We have more files than we had before. We have to make sure to compile the implementation file and the interface file. And notice the order we do things in. We start by IO stream because it is going to be dependent upon by these module and implementation files. After that, we compile the module and we compile the implementation, which is going to be depending on the module. And after that, we compile the main CPP file, which depends on all these things that we compiled before. This order is really important. Notice that it is the same thing we do with Clang. We start by IO stream, we compile the BMI. After that, we compile the module. After that, we compile the implementation. And then we try putting everything together. We put together the main object file. We put together the module file, and then we put everything together into our rooster binary. You really have to understand this. Now that we know this, we can hop over into our IDE and try to use the G++ compiler. If you don't want to go through these steps, you can just stop here and watch the next lecture, because the remaining part of this lecture is just going to be using different compilers to do what we just did inside Microsoft Visual Studio. So let's go back and use GCC. Let's open a terminal window here. So let's do terminal, and this is going to give us a few terminal windows we can use. They will be already open in this folder here, so we can just do ls to see the content. Again, the meat of this project is made up of these three files: main.cpp, math.ixx, and mathimpl. Let's try to compile this with GCC. So we compile the IO stream header unit. This is going to go through. We compile the module file. This is also going to go through. Let's do that. We compile the implementation file. This is the command you use to do that. And we can compile the final binary by putting together all the files to create a rooster.exe binary here. Let's copy this and come back to our terminal inside Microsoft Visual Studio. Run the command. This is going to generate our rooster executable. If we do ls, we should see it right here, and we have the option to run it, and if we run it, we will get the output that we expect here. This is the process to compile and run the code using the Clang compiler on Windows that I have installed. Let's see how you can do this with Clang as well, because we have access to a Clang compiler. Let's copy the command. We will be using the command prompt for this for reasons you already know. We have seen these reasons in the first few videos of this chapter. Let's do ls and clean up. So let's remove any object files that we have. We can do that like this, and remove rooster, and remove the GCM folder that is generated by GCC, GCM, and this is going to go away. Let's hop over to our command prompt. Make sure we grab the first command from our instructions for Clang 16 here, and we can paste it in inside command prompt. So let's do that. Paste, and this is going to compile our header unit. We compile our module into a PCM file. That's what we are about to do here. Paste in the command. This is going to give you the PCM file. Go back, grab the command to compile the implementation file. Again, you can notice that it is the same order that things were built in inside the IDE when we used the tools from Microsoft. So you can use that as a way to cheat and see ideas from some other people if you are into that kind of thing. Let's put in the command to compile our main file into an object file. Grab the command to compile our module file into an object file. This is what we do with Clang. And we need to do the last thing, which is going to put everything together and generate a rooster binary. Copy and come back and put that in here. And this is going to give us our binary. If we do dir in command prompt, we should have a rooster.exe binary. If we run it, it is going to give us the output that we expect here. These are the steps you should follow to compile with Clang on Windows. We will also use our Docker container because we have access to it. Before we do, let's see what we have here. Let's do lsalh to see everything in a nice list. Let's remove any PCM files. Let's remove any object files, and let's remove rooster. And this is going to give us a clean slate to start with. And we can run our commands. Again, let's copy from our README file here. We will compile the IOStream header unit. It is done. Let's compile our module into a PCM file. This is something we need to do here. Okay, this is done. Let's go to compile the implementation file. And this is done now. And the next thing we compile is going to be the main file into an object file. And this is going to go through, grab the command to compile our module file into an object file. And the last thing is going to be to put everything together. So copy the command and paste that in our terminal here. And this is going to give us our binary. If we do lsalh, we should see this in a nice list. And if we run it on Linux, it is going to give us the output that we expect here. This is how you can separate the interface from the implementation and store the implementation in a separate file. I would recommend you carefully watch the instructions we pass to compile, especially now that we have multiple files. For G++, we had to compile the implementation file into a CPP file. For Clang, we also have to do the same thing, and notice the command here. And I figured out these instructions by reading the documentation for compilers and really fighting my way through to get this working. If you have any problem, please do ask. I will do the best I can to help you out. This is all I have to share in this lecture. I am going to stop here, and I will see you in the next one. In this video, we are going to continue on our quest to separate things, and we will go one step further and separate our interface across multiple interface files. This is something you may want to do if, for example, you are developing the same module, but it is a team of people that are working on the same module. So person B is working on another part and they need to put everything together. You can use this technique to put your code together. Let's look at the code because that's the best way to explain these things. Again, we have the same module we've had before. We have our declaration here. We have our purview. We have our preamble down here, and we have our purview, which is going to contain the interface that makes up this module here. We have a bunch of functions and we have a class. Now, what we are going to do is to separate this into two implementation files. The first implementation file is going to contain math-related stuff. That's why we call it math_impl. And it is going to have the add function and the definition for our point constructor here. Notice that it is the same old structure we follow. We have a module, we have the module declaration, which is really not a declaration here because this is an implementation file. So all this line is saying here is that this file is part of the math stuff module interface. We have the preamble. If we wanted, we could import stuff here, and we have our implementations that make up the purview of this file here. We also have another file which is going to contain print related stuff. Again, we have a module, we have the declaration, and we have our purview. And it is going to contain the greet function and the print name length function here. And using this technique, you can have as many implementation files as you want. That's going to depend on what you are trying to build with C++. Now that you have seen this, let's head over to our IDE and see this in action. Okay, here we are inside Microsoft Visual Studio, our IDE. The code we will be compiling will be coming from the GitHub repository. The current project is 48.6 right here. So these are the files that make it up. We have a main CPP file. We have our interface file. We have math_impl and print_impl as our implementation files. These are the files that are going to make it up. Again, And these are the instructions we will be using to compile on Visual C++. Visual C++ is going to give a nice experience in that you don't have to compile yourself. The tools are going to take care of figuring out the dependencies and compiling our module files in an order that will make things work. For GCC and Clang, the story is different. We have to compile ourselves, and we have to make sure we compile things that other files depend on first. That's why we compile the IO stream header unit first. After that, we do the module. After that, we do implementation files. And after that, we put everything together. The same story applies to Clang. So you can see that we are compiling the header unit first. We do the module files. We do the implementation files. And then after that, we put everything together as we do here. For Clang on Windows, we don't pass this flag because we don't want to use the Clang standard library, but on Linux, we make sure to do this. This is something we have done a lot of times. Take a moment to notice the commands we use to compile here if you care about this. This is something that confuses a lot of people. I had to do a lot of research to put this together. And you can learn from this and adapt this to whatever structure you have in your project if you want to use these kind of things. Let's hop over back to our IDE and add in the files that we need. Let's click and add a math. What did we add? Source.cpp. We don't want source.cpp, but we can rename this to be math_impl.cpp. This is going to do. Let's add another one. So let's add a new file. It's going to be a CPP file as well, and it is going to be print_impl. I think this is the name we used, and we need to add our interface file. Let's do that. Add new item. It's going to be a module file, and it is going to be math.ixx. Now we have the files that we need. We can hop over to the repository and grab the interface file. That's where I like to start. We can copy raw file and come back to our editor, do the interface file. So copy and paste. This is done. This is a module file. We have to make sure we have export module and all this syntax that we have here. Let's go back and do math_impl. So it is opened. We can copy raw file. Let's come back, math_impl. That's the file of interest here. Let's go back and compile print_impl and copy. It is copied. Come back and put it in print_impl. It is a module implementation file, and we can hop over to the main CPP file and put in the content. So main.cpp, it is going to import the module and use it. Nothing special here. Copy, it is copied. We can come back and put in our code. Now that we have this, we have to make sure to enable Cplusplus20 before we try to compile. Let's go to language here and enable Cplusplus20. And we need to come into general here and scan the sources for module dependencies. And we say yes, apply, okay, and try to build. Let's see what we get. Seems like the build is good because we have succeeded here. But again, notice scanning for dependencies. It is going to look at what files that we have. After that, it is going to start compiling. Notice the first thing we compile is IO stream because it is needed by other files that depend on it. After that, we have math. After that, we have our implementation files and the main CPP file. And we can run our application by going to debug and start without debugging. And we will see our output here. This is how you can separate an interface into different implementation files. We have compiled using the IDE from Microsoft. Now, the next thing we want to do is to compile using the other compilers, namely Clang and GCC. If you don't care about that, you can move on to the next lecture, but I strongly encourage at least to watch how these things are done because you may need to do this sometime. You never know. Let's go back to our repository, the readme file, and we are going to compile with GCC first. Again, we can learn from the compilation order we saw in the IDE and follow that order. You can peek and cheat and learn. There is nothing wrong with that as long as you don't steal other people's work. So let's go to PowerShell, do ls, and see the content. Again, the meat of this project is this set of files that you see here. The rest that you see on top is just the noise from Microsoft Visual Studio. And we will ignore this for the moment. We will be compiling using G++. Let's put in the command to compile our header unit. It is going to go through. We can compile the module file. We steal the command to do that. And we put that in place. We grab the command to compile our math impl file. This is going to compile it into an object file. We also grab the command to compile the print impl file, and we will put this in place. And you can do ls at any point to see what was generated by the command you just run. And I am going to grab the command to compile everything into the rooster binary that we are waiting for. And if we do that and do ls, this is going to show our rooster file that was generated, and we can run it, rooster, and it is going to give us the output here. This is how you compile using GCC on Windows. Let's use Clang on Windows. Again, this seems repetitive, but you may need to do this, and I want you to be able to adapt these commands to do whatever it is you want to do. If you don't care about this, feel free to move to the next video. Copy the command to compile our header unit, but before we do, let's clean up the mess we left from GCC. So remove the GCM folder, remove any object files that was generated, and remove the rooster binary. If we do ls, we have our starting files here. Let's go back to the command prompt because we are using Clang on Windows, and this is going to generate it. Again, copy all these commands. Bear with me, this may be boring, but it is what we need to do to understand these things. Put in the command. Grab the next command, which is going to compile the implementation file for math impl. Let's do this. This is going to compile. Let's grab the next command to compile the print impl file into an object file. I put it in and hit enter. Let's grab the next command, which is going to compile the main file into an object file. So you can do this, and it is going to go through. And let's grab the command to compile our module file into an object file. This is what we need to do here. And we grab the last command, which is going to compile our rooster binary by putting everything together. Let's do that. And we have our rooster binary. ls is not going to work because we aren't on PowerShell. But we have our rooster binary generated using the Clang compiler on Windows. Let's run rooster, and we will see the output that we expect here. I couldn't stop without showing you how to use Clang 18 under our Docker container. So let's clean up the mess that was left in by Clang on Windows. Let's remove any PCM files, remove any object files, and remove rooster. Once we do that, we will have a clean slate to start by, and we can copy the commands. Again, I will be copying the commands and pasting them in. You can follow along if you want, or you can just watch me do this. It's also helpful. So let's put in the command to compile our header unit. Let's put in the command to compile the PCM file for our module file. The next command is going to be to compile our math impl file into an object file. Notice that for Windows, we are using the C++ standard library that comes with Clang. We do that through this stdlib setting here. Make sure you see this. And if you don't understand this, you can search this flag and you will have more information on the internet. You are a good C++ developer if you made it If you made it this far in the course, congratulations. We compile our main.o file, and we compile the module file into an object file before we put everything together to generate our rooster binary. So let's do that. Copy and paste the command to do that. And now we should have our rooster binary. Let's show this in a nice list. We can see our rooster binary right here. And if we run it, it is going to give us the output that we expect. This is really all I had to share in this video. The main point is that you can separate implementations for your interface in separate files. If you want to compile this on different compilers, these are commands you can use. Please feel free to adapt them to whatever you need. I am going to stop here in this video and I will see you in the next one. In this video, I want you to see that you can separate everything into a lot of interface files and have interface files import each other to really have a big project. We will take the same project we had before and break it into two interfaces. We will have a math stuff interface that we always had, but we will also have a print interface, which is going to have a print related functions in our program here. Let's show you the interface file for math. It is going to have the add function and the point class. This is the interface we have. Notice the module declaration. It is the most important thing if you ask me. Make sure you see the global module fragment, the module preamble, and the module purview. These are words you need to be able to understand to communicate using C++ 20 modules, to talk to other developers and express your ideas. And we have the print interface file. Notice it is a new interface that we are introducing because we have the declaration here, export module print. Don't forget the semicolon here. And it is going to export the two methods that we have here, greet and print name length. And we can set up implementations for these interfaces. The file we have here is the implementation for the math staff interface. That's what we are saying here. It is going to import the other interface. It is going to import the other module that we just defined. Isn't this cool? And it is going to use it by calling the greet function here. And this is going to fall in place and work. Let's look at the implementation for the print interface. It is right here. Again, it has two functions, greet and print name length, and it is going to work. Notice that the includes are showing up in the global module fragment. This is a practice you should follow. You shouldn't have any preprocessor related stuff anywhere else. You should put all that in the global module fragment, and your code is going to work if you happen to need this. This is really all we are up against in this video. Let's head over to our IDE and see this in action. Okay, here we are inside our Microsoft Visual Studio IDE. I created the project and we need to go back to the repository and see the files that we have to deal with here. Now we have the main CPP file, the math interface file, the print interface file, and the two implementation files because we are breaking everything in two interfaces, the math interface and the print interface. Our project is made up of these files that you see here. Again, it is a repetition of what we have seen. We have instructions to compile using the Visual C++ compiler. You can see them right here. And these are the instructions to compile using the GCC and Clang compilers. Notice the order we compile things in. Again, we will start by the header unit. We will compile the interfaces, and we will compile implementations that depend on these interfaces. And after that, we will put everything together to create our rooster binary. The same ideas apply. IO stream, the math interface, the print interface. We put everything together to create the implementation files. You can see them right here. And we build our object files and put everything together to have a final binary that we can run. Let's do this inside Microsoft Visual Studio. The first thing we need to do is to create the files. So let's add our interface files. So the first one is going to be math.ixx. The second one is going to be math. The second one is going to be print.ixx, the interface file. So let's do that, print.ixx, and we will add the implementation files. So let's look at the names to make sure I don't mess up here. We have math.impl and print.impl. Let's do that. So add, it's a CPP file, a C++ file, math_impl. This is the naming convention we have chosen. And we have to add print.impl. So let's do that, add new item, a C++ file, print_impl, and we have to add this, and the rest is really copying code from the GitHub repository and using that in our project. We start by the math interface. Let's copy row, and it should say copied. Let's go to the math interface file. Why don't we have any content predefined in here? Let's see how this is going to go. The math interface file is in. It is a module file, so it is a module interface file, so we have to export module and say the name of the module. Let's do the other module, print.ixx. It is really simple. Copy it and come back to our code, print, delete everything we have in here and put in our module. Again, export module because this is a module interface file. Let's go to math impl, and we copy everything and come back to our IDE, math impl. Let's delete everything we haven't put in, the new content, and we need to go to print impl. Let's copy this and come back to our IDE and do print underscore impl. And the rest is really doing the main file, which is going to put everything together. Copy everything and come back to our IDE and go in the main CPP file. We take out whatever it is we had before and we paste in the new content. Okay, now that we have done this, remember this is a C++ 20 modules project. We have to enable C++ 20 in this IDE that we are using here. Let's go to language and use C++ 20. We have to go to general and enable scan sources for module dependencies. This is needed for our code to work. Apply, okay, and we can try to build. Let's hit the build button here. And the build is going to be good. Congratulations, you have made it. Again, try to learn from this IDE. It is going to scan the dependencies. It is going to find a few files. And after it has the dependencies, it is going to compile in a specific order. Notice that it is going to compile the print interface first. Remember that the math module is going to be using this print interface. So we compile it, we compile IO stream, the header unit, we compile our implementations, we compile math, and we compile main CPP and math impl. This is the order you can follow to compile these things. Now that you have seen how we use this using the compiler and IDE from Microsoft, the next step is going to be using the other compilers that we have access to. This is going to be a repetitive process. I do encourage you watch it, but if you don't want, you can move on to the next lecture because we are not going to be learning anything new. We will be just using these commands on the terminal, but I strongly recommend you try these things out. Compiling things on the terminal is something you may do in your career as a C++ developer. Let's copy the command for GCC. And I need to go to PowerShell inside our IDE here. So let's go to View Terminal. I will have PowerShell here. Let's do ls. It is going to show me the main files in our project. Again, what we care about is this set of files. The rest here is the noise from Microsoft Visual Studio. We don't really care about that. Let's run the command to compile our header unit. It is going to go through. Let's compile our interface, the math interface file, put in the command. We grab the command to compile the print interface and put it in place. We grab the command to compile the implementation file for the math module. Let's make sure we grab it correctly because I don't want any typos here. And you don't have to memorize these commands. Make sure you have them somewhere so that you can copy from them. What I do in this chapter is really what I do in my career when I am working on projects. You can find me browsing through my repositories, hunting for commands that I can edit because I am really bad at remembering these commands. I have better uses for my time. Now we have the rooster binary generated. If we run it, it is going to do what we need to do. And we have just used the G++ compiler to compile this project that is using functionality spread across modules. And this is really cool. Let's clean up the mess left by GCC so we can remove any object files. We can remove rooster and we can remove the GCM folder recursively, GCM. and it is going to go away. If we do ls, we are clean again. Let's go to the command prompt and use the Clang compiler. So again, we use the command prompt because PowerShell has given us problems earlier. We don't want those problems, but the command prompt can work. Compile the IO stream header unit, put it in place. We copy the command to compile the module file and put it in place. We copy the command to compile the implementation file for math. You see, it's a really long command. I don't think I had a chance to explain these things to you, but when you compile with Clang, sometimes you have to specify the location of the PCM files, and you do that through this flag here. If you are confused by Clang, you can go to your search engine and say Clang C++20 modules in the search engine, and you should have an entry that shows you the documentation for using Clang. I want to try to explain this because this changes across Clang version, and I can't really do a better job than what they are doing here. So make sure you read this if you care about Clang. What I am showing you is just the result of me going through this documentation and adapting the commands that they give here to work with the projects that we have in our course here. So this is something you can do if you are interested. Let's go back and compile. This is going to give us the implementation file. Print PCM not found. Why is that? Why is that? I may have lost my train of thought here. Print PCM. We didn't compile it. So let's compile print PCM first before we attempt to do this. Okay, let's grab it and compile it. So print PCM, now it should be available. Let's go down and compile the other one, which is going to be the math implementation file. And put in the command. This can be a tedious process, and if you come across errors, you're going to be pulling a lot of your hair. That's why I gave you these commands here. Okay, so this is done. Let's go to the other command, and it is going to be compiling our main file into an object file. Let's do this. And we can go back to compile the math stuff object file. And we can grab the command to compile the print file into an object file. And we are finally at the end. We needed to compile to see our rooster binary. And if we put it in, hopefully it's going to work. And it seems that it worked. dir on the command prompt, we will see our rooster binary and we can run it. Okay, and it is going to give us the result that we expect. This is how you can compile this project using the Clang compiler on Windows. We can now look at how we can do the same using the Clang compiler that lives in my Docker image. Let's ls to see what we have. Let's remove the junk that was left in by Clang on Windows. Let's remove any PCM files, remove any object files, and remove rooster. And we should be clean now. And I will be copying all these commands one by one. Bear with me. This is a tedious process, but you have to do it to be able to understand how these things work. We compile our header unit. We compile the math stuff. We compile the math interface file into math_stuff.pcm. This is the command. You will get a warning here that you will ignore. Let's put in the command to compile the print PCM file. Let's grab the next command and put that in place. It is going to be compiling math impl. Let's put that in our PowerShell window, terminal window. And we can go back and grab the command to compile our print impl file. Bear with me, this may be boring, but it is how you learn, my friend. Let's put in the command. The command is going to be compiling math stuff here. So this is what we need to put in. Grab the command to compile your print PCM file into a print object file. This is what we are doing now. Put in the command, hit enter, and we need to do the last thing, which is going to put together everything to generate our rooster binary that we have been waiting for. We have our rooster binary, as you can see right here. Where is it? It is here. And if we run it, it is going to do what we want it to do. This is really all I wanted you to see in this lecture. I hope you found it useful. I am going to stop here, and I will see you in the next one. In this video, we are going to see that you can import something and export it at the same time. Let's show you what I mean. Here we have a module file which is going to wrap around a point class. This is going to be representing a point in a two-dimensional space, nothing new here. And it is a point class, but we can use this to set up a line class. And as you may already know, a line is made up of 2 points. So here we have a line class which is going to be made up of 2 points. This is a class we are modeling, but the main point here is that in this line module, to be able to use the point module, we have to import it, and it is what we do here. But at the same time, we are exporting this module to be used by other people who may have imported the line module, because by default, what I import in my module for use is not exported for other people that import my module. In other words, just because you imported a point from line here doesn't mean that if you import line, you get access to point. But by importing here, we are making sure that anyone who imports line will have access to point and will be able to use it. This is the main idea in this video here. Once you have your modules defined, you can head over in the main file. You see we are only importing line, but we will have access to point and be able to use it. Let's head over to our IDE and see this in action. Okay, here we are in our IDE. The project is 48.8 export import. We will be creating our files. Let's go to the repository and see the files that we have to deal with. I would recommend you read the README file here and see instructions on what makes up our project and what instructions we have to compile the files using any of the compilers that we have supported here. And we have a few files, line.ixx and point.ixx. Let's create these files here. So we want to add a new item. It's going to be a Cplusplus file, a Cplusplus module file, and it is going to be point.ixx, and we need to also add line.ixx. Let's do that. Line.ixx. We have this in place. We have the main CPP file which is going to import all these files. We can head over to line or point. Let's start by point because it is simpler. Copy. Let's go back to our IDE and use point, delete, and put in the content. Again, make sure it is export module point. This is going to define a point module. Let's go back and grab line, and we copy, and we put the code inside our line file, delete whatever it is we had in, and paste in the new content. Head over to the main CPP file and put in the content as well. Main.cpp, we copy it. It should say copied. Come back to our editor, remove whatever it is we had in, and put in the code. Again, this is using Cplusplus 20 modules, so we have to enable Cplusplus 20 for this project. Language, Cplusplus 20 here. It is what you should choose. And go to General, scan sources for module dependencies, and you should set this to yes. Apply, okay, and if you build, this should build. Okay, build successful, and we can run this project. Make sure you see the order things are compiled. Then again, we compile IOStream again. After that, we compile point because line will depend on point. So before we compile a line, we should compile point first. That's what we do here. We compile line, then we compile main.cpp. Now that you have seen how to do this using this IDE, if you don't care about GCC or Clang, you can move on to the next lecture. But I am going to show you how to compile with these compilers because I really like it. I think it's fun. It is a great way to learn about these things here. Let's go to the instructions for Clang. You can take a moment to read through them and really see the order. For example, for GCC, the F modules TS flag here enables C++20 modules. And we pass the C++ system header here to tell the compiler that this is a system header we are compiling. Again, if you want to learn more about these flags, you should read the documentation for your favorite compiler. Here, I am just going to give you the bare minimum to compile the files that we have here. Let's grab the command to compile our header unit. We copy it, come back to our IDE, and show the terminal by coming to View and hitting Terminal. We go to Developer PowerShell here and do ls to see what we have inside our project. We have our line module, our point module, and the main CPP file. We can compile our header unit. If we do that, this is going to create a GCM cache header folder. If we do this, this is going to create a GCM cache folder, which is going to be containing all these header units. Let's go back and compile the point module. So let's copy the code, the command, come back here and put it in. Let's go back and compile the next module file, which is line.ixx. We come back here and we use the command, and the last one is going to put everything together and generate our binary. Let's copy and put that in place. And if we compile, we should see rooster here. And if we run it, it is going to say whatever is said in our main file. Before we do any more, let's go to line and make sure we are not importing here. Let's suppose we are only importing. And if we do this and try to compile again, let's see what changed. Only the line file changed. So let's try to compile again and see what we get. So let's go to line here and do G++ and whatever is needed there. If we try to compile it, let's see what we get. It is going to compile because there is nothing wrong with it. But if we try to compile main again, you see what happens. In main, we are trying to use the point class. This class is part of the point module, but we are not importing the point module. You can expect something to go wrong, but let's try using GCC to see this, and it is going to give you a bunch of errors. This is what you can see. Even if we try to compile using the compiler from Microsoft, it is going to give us a bunch of errors. You see 1 failed, 0 succeeded, and it is not going to give us, it is going to give us a bunch of errors that you can read through if you want. So if you want this to work, say export import, and it is going to import and export this for use by whoever might import the line module. Let's build again using the IDE from Microsoft. You can see that it is building. We can start without debugging to see our output. And if we compile again using the G++ compiler, let's go back and grab the commands. This may be tedious, but we need to do it. You really need this experience. Even if you do it once, it is going to help you out in your career as a developer. Many people will overlook this, but they really shouldn't. That's my opinion here. So let's compile the rooster binary, and it is going to probably go through. And if we have a problem, we'll try to fix it. Now the compilation is good. We can run rooster, and it is going to go through. Now that we have seen GCC, we can look at how to use Clang on Windows. Again, it is going to be through these commands that you see here. Let's copy the one for Clang 16. For Clang 16 on Windows, we have to remember to use the command prompt. Don't use PowerShell. Otherwise, you will have problems and you will pull your hair. You don't want that, do you? Let's see dir to see what we have in there before we even do anything. I hop over to PowerShell so that I can clear my mess here. Let's remove any object files, remove rooster, and remove the GCM folder because we don't want that. Now we can head over to command prompt and use the first command here to compile our header unit. So copy it and put it in place. And we grab the command to compile the point module. Notice that here we are using the name of the module. This is very important for Clang. We don't compile this into _point. Okay, we are using P because the name of the module starts with uppercase P. You really need to see this. This is important for Clang. So let's copy this and put that in place. So we can come here and compile our PCM file. And we need to compile the line PCM file again. So let's do this. Put in the command. Let's go back and see the next command. It is going to be generating the object file for the main file, the entry point file here. So let's do that. Let's grab the command to compile the point object file. Put it in. Let's grab the command to compile the line file into an object file. And the last command is going to put everything back together to generate a rooster binary. Let's copy that and put that in place. And this is going to give us our rooster binary. If we do dir, you will see it listed here. And we can run it by saying rooster, and it is going to give us the output that we expect. We have successfully used the export import feature, and you can use it if it makes sense for whatever it is you are building with C++. Let's hop over to our Clang 18 living inside our Docker container. Let's do ls to see the files. You can list this in a nice way using the ALH option. And let's clean up, remove any PCM file that we don't want. Remove any object files and remove rooster. And if we list again, we should have a nice list of things that make up our project. Again, the meat of this project is made up of this set of files, main.line.ixx, main.cpp, and point.ixx. The instructions to compile with Clang 18 are here, so all we have to do is copy these commands and paste them in one by one, which is what we are going to do. So let's copy this. The second one is going to be generating our point.pcm file. We put this in, hit enter, grab the next command, which is going to be compiling our line module into line.pcm, the BMI format for Clang, if I can say it like that. Let's go back and compile the main file into an object file. And we need to compile object files for our module files. So we start by point and we put this in. And we grab the command to compile line.o. We copy this and put that inside our terminal. And we grab the last command, which is going to be compiling the final binary. So let's do that and put that in place. Hit enter, do ls. We have our binary generated right here. And we can run it by saying rooster, and it is going to give us the output that we expect. You can try to remove the export here and see the errors you get with Clang, but I am going to leave that to you as an exercise. This is all I had to share in this lecture. I hope you found it interesting. I am stopping here, and I will see you in the next one.